MOSFET has three terminals: gate, drain, and source, and operates like any switch with on-state and off-state. In the off-state, the MOSFET acts like an open switch, preventing current from passing through. This means that no current flows between the drain and source, as the voltage between the drain and source VDS is high. This occurs when the gate-to-source voltage VGS is lower than the threshold voltage. In the on-state, the VDS drops to nearly zero, and the MOSFET acts like a closed switch, allowing maximum current to flow from drain to source. The on-state occurs when VGS is higher than the threshold voltage. Let's take a quick look at the different types of power losses in a MOSFET. Assume that the MOSFET is already in the off state and we need to turn it on. There will be losses during switching on the MOSFET. So every time a MOSFET is switched on, some energy is dissipated in this process, and that's the first type of losses. Now the MOSFET is already on. There will be losses during the conduction phase, and the path between drain and source is a resistance called RDS on. And this is the second type of losses. When turning the MOSFET off, energy is again dissipated. This is similar to the turn on losses, and this is the third type of losses. The energy dissipation during both the turn on and turn off of the MOSFET is called switching losses. So we have two types of losses: switching losses, which include both turn on and turn off, and conduction losses. Therefore, we can simply say that the total power dissipation of a MOSFET is the sum of 1, 2, and 3. There are also additional losses related to gate charge, reverse recovery, output capacitance, dead time, which are not included in this basic model. Let's briefly examine the relationship between VDS and drain current waveforms to understand the two types of losses while calculating the total power dissipation of a MOSFET. Taking it step by step. When the MOSFET is off, VDS is high, as this is the blocking state, while ID, the drain current, is low, as there is no current flows at this point, so the power dissipation is zero. But when turning on the MOSFET, the current ID starts to rise, but VDS does not drop immediately. VDS starts to fall once the current reaches its full value and falls to nearly zero. During this transition, power is dissipated, as shown here in blue, which creates an energy spike. Look at this triangular spike. The area under the triangle represents the energy dissipated during turn on. This triangle is formed by the rising current curve and the falling voltage curve. This energy then can be calculated as ID on times VDD times the total time of the transition divided by 2. The total time is the time it takes for the current to rise plus the time it takes for the voltage to fall. Well, the E turn on, the calculated energy here, is not yet the turn on power losses. To get then the turn on power losses, you need to multiply this energy by the switching frequency, as this determines how many times per second there will be turn on energy dissipation. Well, now the MOSFET is turned on. Then the next type of losses is the losses that occur during the conduction phase, which is the conduction losses. As we explained earlier, when a MOSFET is on and conducting, the path between drain and source has a small resistance called RDS on. So the power loss here is just like in any resistor, I squared R. But the conduction loss equation here is still missing a factor, since the conduction losses occur only when the MOSFET is on, which means in conduction mode, then it's fair enough to calculate this equation only when the MOSFET is on. Therefore, we need to multiply the conduction loss equation by the duty cycle. As you see from this equation that the conduction losses depend on RDS on value, then it's critical to choose a MOSFET with low RDS on. Now let's have a look on the last type of losses, turn-off losses. It works the same way as turning on process, but in reverse. When switching off the MOSFET, voltage rises while current is still flowing. When the voltage between the drain and source VDS reaches the value of VDD, the current starts to drop until it reaches zero. That overlap below the two curves which lead to energy loss, and it's calculated in the same way as E turn on. And just like turn on losses, we multiply this energy by the switching frequency to get the total turn off power losses. By adding conduction and switching losses, we can estimate the total power dissipation in a MOSFET, regardless of the circuit topology. Understanding these losses is a key to improving efficiency in power electronics. Whether you are designing power supplies or motor control circuit, the more accurately you can model and minimize these losses, the more reliable and thermally optimized your design will be. So that's a quick breakdown of a MOSFET power losses. If you found this video helpful, make sure to like and subscribe. Thanks for watching and see you in the next video.